The moon is lying to you. It has been lying to every human who ever looked up, for every night of every century, showing you the same polished face, while hiding something so strange, so fundamentally different on its other side, that when the Soviet Union finally got a look in 1959, the engineers receiving the signal weren't even sure what they were seeing. For all of human history, we've gazed at the moon and assumed the rest of it looks more or less like what we can see. Craters, dark, smooth plains, the familiar shapes that ancient cultures turned into rabbits and gods and old men. It seemed reasonable. Why would one side of a rock be dramatically different from the other? But the moon is tidally locked to Earth, meaning it rotates at the exact same rate it orbits us. One full spin equals one full trip around the planet. The result is that 41% of the lunar surface has never, not once, been visible from anywhere on Earth. No telescope could reveal it. No observatory could study it. For millennia, it was the closest piece of true unknown in the entire sky. And then the Soviets decided to go look. October 4th, 1959. 2 years to the day after Sputnik shocked the world, a rocket launched from the Baikonur Cosmodrome carrying a small cylindrical probe called Luna 3. It wasn't much to look at. About 130 centimeters long, covered in antennas and thermal shutters, packed with a camera, film processing chemicals, and a scanning device that would need to work flawlessly at a distance of hundreds of thousands of kilometers from the nearest human. The mission was so ambitious, so unlikely to succeed, that the Soviet government didn't even mention the far side photography goal in their official announcement. They simply called it an automatic interplanetary station and left it at that. The plan was absurd by the standards of the time. Luna 3 would swing behind the moon, use a photocell to detect the sunlit far side, stop its own spin to stabilize itself, then photograph what no one had ever seen, using actual photographic film, not a digital sensor, not a video feed. Physical film inside a tiny spacecraft, 65,000 kilometers from the lunar surface. And it gets stranger. The film itself was American. Soviet engineers had recovered radiation-resistant 35mm stock from downed CIA reconnaissance balloons, part of a secret program called Project Genetrix, and loaded it into their own spacecraft. Captured enemy film, repurposed for the most audacious photograph in history. After the pictures were taken, the film had to be developed inside the spacecraft. There was a miniature chemical processing lab aboard Luna 3, a darkroom the size of a thermos, that developed, fixed, and dried each frame automatically. Then a cathode ray tube projected a tiny spot of light through the film onto a photomultiplier, which converted the image into an electrical signal, line by line, like a fax machine transmitting across the void. The scanning resolution maxed out at 1,000 lines per frame, roughly equivalent to today's high-definition video. Impressive on paper. In practice, the mechanical scanning, film grain, and analog transmission introduced so much noise that the final images looked more like smudged charcoal sketches than photographs. The trouble started almost immediately. When engineers in Crimea established contact, the radio signal was only half the expected strength. The probe's internal temperature was climbing dangerously, threatening to ruin the film before the camera even fired. They scrambled, adjusted the spacecraft's spin axis relative to the sun, shut down non-essential equipment, and managed to drop the temperature from 40 degrees Celsius back to a survivable 30. It worked, barely. And on October 7th, the camera sequence triggered automatically. 29 frames, 40 minutes. 2 lenses, 1 wide-angle and 1 telephoto, capturing 70% of the far side from a distance that made the images grainy, blurry, and smeared with electronic noise. But they existed.
Now came the hardest part. Getting them home. Not physically, the probe would never return. The images had to be transmitted by radio across nearly 470,000 kilometers of space, picked up by a modest tracking station on the slopes of Kochka Mountain near Semez on the southern coast of Crimea. The station wasn't much. Engineers worked out of tents and trailers, sleeping in rickety barracks near the Black Sea, battling interference and telemetry dropouts around the clock. Even Jodrell Bank, the massive British radio telescope, with an aperture nearly 10 times the size of the Crimean station, tried to intercept the signal. The graduate students working for Sir Bernard Lovell managed to capture a transmission on 183.6 megacycles, but they'd narrowed the receiver bandwidth so aggressively to filter noise that they clipped off most of the actual image data. Their recording showed something, but whether it was a photograph of the moon or a test pattern was, honestly, hard to tell. The first 4 Soviet transmission attempts, starting on October 8th, returned nothing usable. The signal was too weak. Luna 3 was near the farthest point of its orbit, nearly 500,000 kilometers from Earth, and the images dissolved into static. Sergei Korolev, the chief designer of the Soviet space program, whose identity was kept secret from the outside world, flew to Crimea personally with a small team of engineers on a military jet. He mobilized the Air Force, Aeroflot, the Communist Party, and the Soviet Council of Ministers to support the effort. They waited. They listened. They adjusted. Korolev arrived so late to the flight that the plane had to interrupt its taxi to let him board. On the 5th attempt, as the probe swung closer to Earth, 2 usable photographs finally emerged on the thermal paper printouts. Blotchy, monochrome, barely legible, but unmistakable. By October 18th, a total of 17 frames had been received. On October 22nd, all contact with Luna 3 was lost forever. The probe eventually burned up in Earth's atmosphere sometime in 1960, carrying its undeveloped frames, its tiny darkroom, and its stolen American film into oblivion. And when the scientists at the Sternberg Astronomical Institute in Moscow analyzed what those 17 surviving images showed, the excitement turned into confusion. The far side looked nothing like the near side. Where the familiar face of the moon is covered with broad, dark volcanic plains, the far side had almost none. Instead, it was a battered, cratered wasteland. Mountains, ridges, impact scars layered on top of each other, stretching across the entire visible surface. The Soviets identified only 2 dark regions, and they named them immediately. Mare Moscoviense, the Sea of Moscow, and Mare Desideri, the Sea of Desire. That second one would later turn out to be a collection of smaller features, not a single mare at all, but the naming rights were theirs. Luna 3 saw it first, and in lunar cartography, whoever sees it gets to name it. That's why so many craters on the far side carry Russian names to this day. One crater stood out. Over 160 kilometers wide, with high terraced walls sweeping down to a dark mare floor and an astonishing W-shaped central peak. They named it Tsiolkovsky, after the father of Russian spaceflight. Apollo astronauts would later use it as a visual landmark to orient themselves over the far side, the one recognizable anchor in an otherwise unfamiliar gray expanse. The asymmetry between the two hemispheres was stark. On the near side, about 31% of the surface is covered by maria, those dark plains of cooled basaltic lava. On the far side, it's roughly 1%. The far side is actually brighter than the side we see, because there's almost no dark volcanic rock to absorb light. If anything, the dark side is the bright side. The name itself is a misunderstanding. Pink Floyd didn't help. So why are they so different? This mystery has a name. Scientists call it the Lunar Farside Highlands problem. And it's been debated since those first blurry photographs arrived in Moscow. The Soviets published an atlas within a year, but the explanation would take decades. The leading theory traces back to the Moon's birth. About 4.5 billion years ago, a Mars-sized body called Theia slammed into the young Earth, blasting debris into orbit that eventually coalesced into the Moon. At that point, the Moon and Earth were 10 to 20 times closer than they are now. Both were molten, glowing, radiating extreme heat. And here's where it gets specific. The Moon became tidally locked to Earth almost immediately. That means one side permanently faced a planet whose surface temperature exceeded 2,500 degrees Celsius. The near side was baked. The far side faced the cold of space. That temperature difference mattered enormously. The Moon's crust is made largely of aluminum and calcium silicates, minerals that are extremely hard to vaporize. On the cooler far side, these elements condensed first, combining with silicates in the mantle to form plagioclase feldspars. Over thousands to millions of years, this process built a thicker crust on the far side. Think of it like frost forming on the cold side of a window while the heated side stays clear. The result was a fundamental structural imbalance baked into the Moon from infancy. The near side crust ended up thin, sometimes thin enough that large asteroid impacts could punch through it and release basaltic magma from below. That magma flooded the impact basins, cooled, and became the dark maria we see tonight. The far side crust, roughly twice as thick, acted like armor. Impacts hit just as hard over there, but the magma couldn't break through. So you get craters on craters on craters, but no flooding, no dark plains, no familiar face to look at, just scars. And the far side holds extremes the near side doesn't. The Moon's highest point and its lowest point are both on the far side. Its tallest mountains, measured from base to peak, are on the far side. The terrain swings between extremes that the smoother, lava-filled near side simply doesn't exhibit, because the near side had its roughness erased by volcanic floods. The far side never got that makeover. It wears every wound it's ever received. This wasn't fully understood for decades. The Soviet scientists in 1959 could see the difference, but they couldn't explain it. NASA's Grail mission in 2012 finally mapped the crustal thickness variations in detail, confirming that the far side crust is substantially thicker. And in 2014, researchers at Penn State published a study arguing that heat from the molten Earth was the key factor, connecting the Moon's asymmetry to the physics of lava exoplanets that orbit dangerously close to their host stars. Our Moon, it turns out, was once one of those scorched worlds. A competing theory proposed that a second, smaller moon formed after the giant impact and later collided with the far side, splattering extra material across one hemisphere. And in 2019, a study suggested a wayward dwarf planet struck the Moon early in its history. depositing 5 to 10 kilometers of debris that became the thicker far-side crust detected by Grail. The truth might involve elements of more than one of these ideas. Nobody has settled it yet. For 60 years after Luna 3, no spacecraft landed on the far side. Orbited it, yes. Photographed it in extraordinary detail, certainly. The Apollo 8 astronauts were the first humans to see it with their own eyes in 1968, swinging around the moon and losing radio contact with Earth entirely as they crossed to the hidden hemisphere. Every Apollo crew experienced that silence. For roughly 45 minutes per orbit, they were cut off from all of humanity, alone with a landscape no human had ever stood on. Communication is the fundamental problem with the far side. The moon itself blocks every radio signal. You can't talk to a spacecraft that's sitting behind 3,400 kilometers of solid rock. For decades, this made a far-side landing essentially impossible. Not because you couldn't get there, but because you couldn't control anything once you did. China solved it. In May 2018, they launched a relay satellite called Queqiao, pronounced Che-Chao, meaning Magpie Bridge, and parked it at a gravitationally stable point beyond the moon, where it could maintain line of sight to both the far side surface and Earth. 7 months later, on January 3, 2019, the Chang'e 4 lander touched down in Von Karman crater, inside the South Pole Aitken Basin. It was the first soft landing on the far side of the moon, ever, by anyone. The South Pole Aitken Basin is the largest, deepest and oldest known impact structure on the moon, and one of the largest in the entire solar system. It stretches 2,500 kilometers across, roughly half the width of China, and plunges 8 kilometers deep. The impact that created it was so violent that scientists believe it punched entirely through the lunar crust and exposed material from the mantle below. If you want to understand what the moon is made of beneath the surface, this is where you look. And Chang'e 4's rover, Yutu-2, found something. The spectrometer aboard the rover detected minerals on the crater floor that were markedly different from anything previously sampled on the near side. Traces of olivine and pyroxene, components associated with the lunar mantle, were sitting right there on the surface, kicked up by ancient impacts. It was the first direct evidence that the moon's interior could be studied from the ground, not through models or remote sensing, but by touching it. The rover also carried a ground-penetrating radar that mapped subsurface layers beneath the landing site, revealing a complex sequence of ejecta deposits, buried craters, and geological structures extending meters below the surface. And in a moment that had nothing to do with geology at all, a small sealed container aboard the lander sprouted cotton seeds, the first plants ever to grow on another world. They died within days when the lunar night brought temperatures plunging to minus 190 degrees Celsius. But for a brief window, something alive existed on the far side of the moon. Then China went further. In June 2024, the Chang'e 6 spacecraft landed in the Apollo Basin, also within the South Pole Aitken structure, scooped and drilled nearly 2 kilograms of soil and rock, loaded it into an ascent vehicle, launched it back into lunar orbit, transferred the samples to a return capsule, and brought them home to Earth. The capsule parachuted down to the grasslands of Inner Mongolia on June 25, 2024, carrying the most scientifically valuable cargo to return from the moon since the Apollo era. The first samples ever collected from the far side of the moon.
When scientists analysed 108 basalt fragments from those samples, the results reframed the far side's history. Most fragments dated to about 2.8 billion years ago, confirming that volcanic activity on the far side lasted far longer than many had expected. One fragment dated to 4.2 billion years, containing a chemistry rich in potassium, rare earth elements, and phosphorus, a signature known as creep, that's normally concentrated on the near side. Finding it on the far side, in an ancient sample with pristine magmatic texture and no impact fractures, suggests that the distribution of radioactive heat-producing elements inside the Moon was more complex than existing models predicted. The younger samples, meanwhile, were almost completely devoid of creep. Something changed in the magma source feeding the eruptions over that 1.4 billion year gap, and nobody is entirely sure what. The far side, it turns out, wasn't just a dead, cratered wasteland. It had its own volcanic history, its own internal heat engine, and its own chemical story that doesn't match the near side at all. We built our understanding of the Moon from 6 Apollo landing sites and a handful of Soviet sample returns, all on the near side. That's like landing in the Sahara Desert 6 times and concluding the entire Earth is made of sand. There's another reason the far side matters, and it has nothing to do with geology. Because the Moon's bulk permanently shields the far side from Earth, it's the most radio-quiet environment in the inner solar system. No television signals, no cell towers, no satellite chatter, no electromagnetic noise of any kind from a planet of 8 billion people. It's silent in a way that nowhere on or near Earth can be. For radio astronomers, the far side is a cathedral, a place where telescopes could listen for signals from the earliest epochs of the universe. Frequencies so faint that Earth's own noise drowns them out completely. Scientists have proposed placing arrays in large far-side craters like Daedalus or Saha, where the combination of radio silence and zero atmosphere could enable observations of the universe's first few 100 million years, the so-called Dark Ages, before the first stars ignited. Chang'e 4 carried a low-frequency spectrometer specifically to test this concept, and the results confirmed what physicists had hoped. The far side is an ideal platform for a kind of astronomy we've never been able to do.
When Luna 3's grainy, streaked, barely legible photographs arrived on those thermal paper printouts in Crimea in 1959, the engineers who received them probably didn't grasp the full weight of what they'd found. They saw a different landscape. Craters instead of plains. Roughness instead of smoothness. They named what they could and published an atlas within a year. What they'd actually uncovered was a 4.5 billion year old scar from the Moon's violent infancy. A record of how heat, gravity, and proximity to a molten Earth shaped 2 completely different worlds on one small body. The far side isn't mysterious because it's hidden. It's mysterious because it remembers things the near side was too hot to preserve. Every crater on that battered face is an entry in a logbook that goes back to the heaviest bombardment period of the inner solar system, a record that the near side's volcanic floods erased long ago. We've only just started reading it. Chang'e 7 is heading to the lunar South Pole in 2026. Chang'e 8 will follow in 2028, testing technologies for a permanent research station. NASA, ESA, and other agencies have their own plans for the region. The far side isn't going to stay quiet for long. Whatever secrets the moon has been keeping for 4.5 billion years, the silence is finally breaking.